So ladies and gentlemen, you are welcome to my YouTube channel. So today we are going to look at how to solve some questions from organic chemistry. Starting with question 1, and please, if this is the first time you are coming to my YouTube channel, please subscribe. So the first question says, what is the IFAC name for the structure below? So we have the structure like this, where we have CH3. First, you need to look at the compound very well and identify the number of the functional group, and which one you would give priority. So you see, in this compound, actually, there are 2 or 3 functional groups. Because whenever you have a single bond between carbon to carbon, that indicate an alkane, and double bond indicate alkene, then triple bond indicates alkyne. So if you have alkene and alkyne functional group, which one are you going to give a priority when naming? The alkyl group with the triple bond is the one that is always given priority. And when you have double bond, in the absence of triple bond, then the double bond will be given priority. And if there are other functional groups like OH group, will give OH group priority than the triple bond. If there is carboxylic group, we give carboxylic group priority in terms of naming than any order. So there is actually an order of naming, or the order of prioritizing functional group when naming, but in this case, the alkyl group will be given, the alkyne that is with triple bond will be given a higher priority. So based on this now, even the numbering will start from the triple bond. The numbering will start from the triple bond. So you know that actually when naming organic compound, first you need to identify the parent chain. That is the longest carbon change in the compound. So if you start counting from here, like for example, this is 1, 2, this is 1, 2, 3, 4, 5, 6. This is, if you follow 1, 2, 3, 4, 5, 6. So it's the same thing. So you can just consider it from this direction to this direction, because this is where we have the triple bond. So therefore, we start numbering from here. We have 1, we have 2, we have 3, 4 here, and then we have 5, and then this is 6. So of course, at position 5, we have methyl, and at position 1, 2, 3, we have 1, 2, 3, 4. Then at position 4, we have double bond. So therefore, what will be the naming? So since it is 6, it means that the functional group or the parent chain will be hexyne. So therefore, now let's look at our substituents. The double bond will be substituents. The methyl group will also be substituents. So therefore, when naming now, we have methyl at position 5. So we are going to have 5. We have 5 methyl. We have also methyl group at 1, 2, 3. So we have methyl at position 3, 2. So we have it at position 3. So we have methyl group at position 5 and position 3. So therefore, when we are going to name this, it is going to be simple. That okay. So we have it at position 3. So we are going to have 3, then comma 5. Between number and number, we use comma. And then it's now going to be, since the methyl are 2, we have it at position 3 and 5. So it's going to be dimethyl. Then what position do we have the double bond? It at position 4. So we are going to have hyphen. So between number and letter is hyphen. So we now have 3, 5 dimethyl. Then we have 4 hyphen hexene. hexene because of the double bond. So here is going to be En. And of course, at position 1, we have triple bond. We have this triple bond. So it is going to be 3,5-dimethyl 4-hexene. At position 1, we have it. So we have 1-ine. So this one will be the name of the compound. So you have 3,5-dimethyl 4-hexed 1-ene. So that is actually the name of this compound. So the answer is option D. So option D is the answer. So then, but before we actually proceed, there are rules in naming organic compound. First, when naming organic compound, you have to identify the longest carbon chain, identify the position of the substituent, number them according to their position, and then if there is any functional group, then understand or know which one to be prioritized. Like for example, here we have alkene, we have alkyne, but the prioritization is given to alkyne because that is the rule. Whenever you have alkene and alkyne, alkyne will be prioritized. So the name of the parent chain will end with the alkyne functional group. That is why here we have ine. So now let's look at another question. So let's move to question 2. So here, what is the formula indicate 2,3,4-trimethylhexane? So we have a compound like this and we want to know exactly the number of carbon that is there and the number of hydrogen. So we want to know the molecular formula. So to know the molecular formula of this is simple. First, you need to draw the structure of the compound. It will be the most simplest way to do that. So it is 2,2,4-trimethyl. It is 2,2-trimethyl. So now what we are going to do, and of course, is hexane. So now, how are we going to draw the structure of the hexane? We know that hexane have 6 carbon. So we have to draw the structure of hexane. So we have the structure like this. So we have 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 5, 6. And of course, between each and every carbon, there is a hydrogen. So we have 2 hydrogen here. Here we also, but before that, actually, we need to indicate the position. Before adding the hydrogen, we need to actually indicate the position. So you see, we have 2,2,4-trimethyl. So it means that this is position 2. So we have methyl, that is, we have CH3. And here we have CH3. And of course, here is CH3. And at position 4, we also have it. So 1, 2, 3, 4. So at position that is position 4, we also have methyl. So therefore, here we have our hydrogen, and here we have our hydrogen. Here we have our hydrogen, and of course, here is 2 hydrogen, and here is CH2. So then, the next thing is to count the number of carbon and the hydrogen that are present. So you see now, let's start. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it means that we have C9. Then we count the hydrogen. We have 3 here plus 3 here, making 6, making 9 here. Then plus this 3, making 9, plus this 2, 10, 11, 12. Then we have 15. We have 15, we have 17. Then we have 20. So it means that it's C9H20. So option A is the answer. So you have option A here to be the answer to this question. So if you have the compound and you are given the name of the compound, then the first thing, if you want to know the exact number of carbon and the hydrogen, then you draw the structure of the compound and you count the number of carbon and hydrogen that are present there. So then let's move to the next question. So now the next question is we have the compound like this. We have CH3, CH2, we have oxygen, then we have CH2, CH3, then we have CH3, we have O, CH2, CH2, CH3R. So we want to know which types of isomers exist in this compound. Is it enantiomers, conformational isomers, metamers, or optical isomers? So first, let's look at what is actually enantiomers. So enantiomers are generally compounds, are pairs of compound with exactly the same connectivity, but they have opposite three-dimensional shapes. They have same connectivity. They are compound with the same connectivity, but they are actually opposite in three-dimensional structure. And generally in the case of the enantiomers, they are mirror image. They are mirror image and they cannot superimpose. And of course, they are they are like optical isomers because they are even in fact they are like types of the optical isomers that have a carbon or that have a central atom that have four different groups attached to it. So that is enantiomers. So generally the best way to describe enantiomers is that they have mirror image and they cannot superimpose. They cannot superimpose and they have the same connectivity but different or opposite three-dimensional arrangement or opposite three-dimensional shapes. That is what we call enantiomers, and they are mirror image and they cannot superimpose on each other. So that is what we call enantiomers. And then we also have what you call conformers or conformational isomer. So in terms of the conformational isomerism, they are actually isomers that can intercombated just by iterations about single bonds. They are the same compound with the same molecular formula, the same structure, the same connectivity, but they can intercombat it by just rotations around a single bonds. So that is actually what we call conformational isomers. And then the next thing that we are going to look at is metamers. So metamers are the isomers with the same molecular formula but different alkyl groups around the same functional group. So like for example, now let's look at this compound. You see we have what we call ether. We have what we call ether. We have what we call ether. So we have what you call ether functional group. So in the case of ether functional group, they have RO, R12 here. So they have two different, or sometimes it may be the same alkyl group. And this is an ether functional group. Ether functional group. So in the case of metamers is when you have different alkyl group around the same functional group. So now let's look at this compound. You see the first one here is CH3, CH2, or CH2, CH3. So this is alkyl group and this is alkyl group. And this is actually is called diethyl ether because we have ethyl here and we have ethyl here. So we call it diethyl ether. That is how to name ether. Diethyl, you start with this and this. So because they are all ethyl, that is why it's called diethyl ether. But look at the other one. We have CH3 or CH2, CH2, CH3. So you see here is Around the O here is methyl. So it's methyl. And of course, we have three, or we have profile here. So we have methyl, profile, pro, methyl, profile, methyl, profile, ether. Methyl, profile, ether, and this is diethyl ether. So we have methyl, profile, ether, and diethyl ether. So if you look at the alkyl group in this case, in the case of diethyl ether, they are the same ethyl group, but in the case, or they are the same alkyl group. But in the case of methyl profile ether, you see that the alkyl group are different. So you see what differ the first compound here and the second compound here is they have different alkyl group around the same oxygen, and that is what you call enantiomer. So it means that option C is the answer. And when we said optical isomers are isomers that, or generally they are compounds. They can only or they can undergo what you call plane polarization, and usually they have what you call L and D isomers. And in the case of optical isomers, they have a chiral carbon, that is the carbon that have 4 different groups attached to it. They have 4 different groups attached to it, that is optical isomers. And in addition, they can be either L isomers, that is laboratory and dextrorotatory. So as we are solving the questions, we are also coming to a point where we'll discuss about the optical isomers. And in addition, if you didn't watch my video on isomerism, I have a video on isomerism, and please try to watch the video. It will actually help you in solving some of the problem. So now let's look at the next question. So we are moving to question 4. So alkenes show geometric isomerism due to A, asymmetry, rotation around a single bond, restricted rotation around a double bond, and then a resonance. So first, we need to understand what is geometric isomerism. Geometric isomerism is the types of isomers that usually exist in a compound that have restricted rotation. So generally, the double bond is highly strong, it's very, very strong, and that is why in the alkenes usually undergo geometric isomerism because of the presence of restricted rotation around the double bond in the alkenes. And that means that from these options, we can clearly see that the option C will be the perfect answer. But in addition, we should understand that geometric isomerism is divided into 2. Geometric isomerism is divided into 2. Geometric isomerism is divided into 2. We have cis geometric isomerism and we have trans geometric isomerism. So if we have a compound with a double bond, like in the case of alkene, they have restricted double bond. So if you have something like this, let's say we have CH3 here, and then we have CH3 here, and let's say here we have chlorine, and then here we have chlorine. So if you look at it here, they are called 6 isomerism because they are the same group in the same plane. They have the same group in the same plane. But in the case of trans geometric isomerism, is when you have the restricted double bond, and then you have, let's say here you have chlorine, and here you have CH3, and then here you have chlorine, and then here you have here you have, let's say here is CH3, and then here is chlorine. So if you look at it, this one is transverse to this, and this one is transverse to this. So that is why it's called trans isomerism. So in the case of cis isomerism, all the methyl group they are in the same plane, but in the case of the geometric isomerism, then the CH group it is transverse to each other. So this is what you call geometric isomerisms, which divided into cis isomerism and trans isomerism, and it usually exists in a compound with restricted rotation around a double bond. And that is why the best way to describe this is to use alkenes, because it has a double bond. So the answer to these questions is option C. As I said, please visit my video on the isomerism, then you will get it better. So then let's look at the another question. So question 5, is it possible to distinguish optical isomers? Yeah, actually, optical isomers, we have L isomers and D isomer. That is laboratory and dextroreportory. But by just mere physical looking, you cannot identify which one is L isomers and which one is D isomer. But interestingly, we know that optical isomers, they have a different effect on plane polarized lights, because you know that light travels in a single plane. So as a result of that, for the optical isomerism, you can use polarimetry. That is polarimeter to distinguish either the compound it is L isomers or D isomers. So polarimetry here is the answer. You can use it to distinguish whether the compound is L isomers or D isomers. So L means laboratory and D means dextroreportory. Like for example, let's look at a compound like this. If you have compound like this, let's say we have CH3 here, and we have NH2 here, then we have H here, and then let's say we have COOH here. And then of course you can have another one here. You can see that here we have CH3, and here we have hydrogen, and here we have COOH, and then we have NH3. No, let me change something, because I wrote this something with some structure. Let's see here, what we have is hydrogen, and then here we have the NH3. You see, if you can look at this, it's like they are mirror image to one another. The NH3 here is at the left, so that is why it's called L. And this one is at the right, and that is why it's called D. So this is dextroreportory and this is laboratory. So this is the optical isomerism. So ladies and gentlemen, this is the end of our videos, and if this is the first time you are coming to my YouTube channel, please subscribe. And you can also check from the YouTube channel, you can join to be the member of my YouTube channel. Thank you.